Hello and welcome back to Engineering Dynamics. I'm your host, Dr. Walk. I have been trying to get my students to understand the difference between these two mechanisms. So here's the first mechanism. Okay, and here's the second mechanism. Both mechanisms, if you look at them, both mechanisms resemble a rigid body, right? Yeah, are they both rigid bodies? Let me ask you this. If I ask you to describe the motion about the point here, can you see that? The point here. If I asked you to tell me or describe what the motion of the point here is relative to this point, would you say, oh, just use your relative acceleration and velocity equations? I hope you would say, no, Dr. Walk, you can't do that. Because if I ask you, if I said this is A and B, what type of body is A and B? Well, it's a rigid body. What type is A and D? What is A and D? A and D is a rigid body. What is A and B? That's a sliding contact. That's a sliding contact. The major difference between, let's say, I don't remember the letters I used. Let's say the major difference between A and B is that the distance between them stays constant. But now, if this is A and this is B, the distance between them, it changes. So our relative acceleration or relative velocity equations that we derived for planar motion of a rigid body no longer holds value. This video is going to go over how we got the relative velocity and acceleration equations for a rigid body, and then compare those to how we're going to develop an equation to deal with this type of motion, to deal with sliding contacts, okay? If that interests you, stay tuned. Okay, so I'm just going to kind of wing this without notes, but we can do it. All right, so the first thing that we're going to look at is a rigid body. I don't care what the rigid body is, but we're going to look at a rigid body, and I want to describe this rigid body's motion as if I'm away from it. Like if I throw a paper airplane, am I looking at the airplane, it's going all around? I just want to describe that airplane's motion by me looking at it, like me just sitting in a chair, I'm fixed, I'm not moving, and I just want to stare at it, and I want to say, how do I describe its motion? What is its translation? What's its angular velocity? What is this airplane doing? Well, in order to do that, I'm going to use relative velocity and relative acceleration. It states that because if you understand, so my airplane, let me back up. So my airplane is undergoing planar motion, right? And planar motion is made up of two different types of motion. It's made up of translation, and it's made up of pure rotation about a fixed axis. So if I want to fully describe the body, it is said that if you can describe one point on the body, then you have fully described translation. And that's because of the definition of translation of a rigid body. Every point inside of a rigid body, it's going to stay that length. So like here, all of the distances between these particles, they're fixed. It's constant. They're never going to change, okay? So if I can explain what this is my position vector, right? I'm going to locate, let's call this point B. If I can explain the translation of point B, then I'm done. But this is an airplane that's flying all over the place and it has rotation to it. In order to describe rotation, I have to find a point in the body that at that moment is zero velocity, okay? I can do that by using relative velocity or the instantaneous center. Right now, I don't have any measurements or geometry written on the screen, so I'm just gonna use relative velocity. To do that, I have to define a second point on my rigid body. Let's label this A. And again, if I'm going to describe the motion as if I'm not on the airplane, right, I have to locate both points relative to my inertial reference frame. So these two position vectors, they're referred to as absolute vectors or inertial vectors. Okay, so to do the pure rotation part, I will have to have some vector locating the points, right? So now when it comes to this part, it's like, I don't know if I'm too old or if you're gonna know what I'm talking about, but You like Honey, I Shrunk the Kids? Okay, well, pretend like I just like shrunk down and I jumped on my little airplane and I'm sitting at point B and I'm looking at A. Well, it's in that viewpoint, it's going to look like A is in pure rotation about where I'm sitting, right? So I can say, I really hope that you know that video or that movie. So I can describe, like I said from the very beginning, my whole objective of this is to describe the position, the velocity, and the acceleration of point A. So I can use vector addition, and I can represent the vector R is equal to RB plus RA with respect to B. And RA with respect to B is equal to some distance in the X plus, this is a unit vector I, plus some distance in the J. And it's really important that right here, this part, because this is going to, that alone is the one thing that changes all the equations. That alone, how we describe X and Y between this one and this one is going to make the world of difference, right? So in a rigid body, so say these two lengths, RA with respect to B, that length won't change, right? And the unit vectors are going to stay constant because we're in an inertial frame. So this means that this is constant. If it is constant, and I take the derivative of this, I can say that RA, the derivative of RA is just the absolute velocity. The derivative of RB is the absolute velocity of B plus the velocity of A relative to B. I can make that connection because everything is constant. I can also, because remember again, the question was to describe the body's motion. We describe the body's motion by using angular and linear terms. So my linear terms are R, V, and A. My angular terms are alpha, omega, alpha, and theta. I wrote that totally in the wrong direction. Let me read that so I don't confuse anyone. So for the angular, it would be angular position, angular velocity, and angular acceleration. So if the reason that you pick 2 points instead of just describing it one, because translation, you only need 1 point. But when we look at the rotation part, we are going to need the 2 points. And that's because if I'm sitting at B, I can say that A is in pure rotation. If I'm sitting on an object, right, and it's moving all over the place, all I'm seeing is that A is just rotating about me. I don't care what is underneath me, what I'm doing, right? Like, because I can't see that. So I can say that VA is equal to VB plus omega cross RA with respect to B. I got the omega cross R with respect to AB because if I look at this position vector, let me use a different color here. We'll use, I'm recording this on Halloween, so it's gonna be spooky. I don't know, I don't even know if green's spooky. Anyway, okay, so if this body is rotating clockwise and A is in pure rotation about B, at that instant, its velocity vector would be VA with respect to B, and it is perpendicular to its position vector and tangential to its curve, right? Okay, so let's look at this. RA, if like my finger's RA and this finger is VB, then my thumb has to be the axis that they rotate about, right? So now if I say RAB and the axis that I rotate about, which is the omega, if I cross these two, I get the perpendicular. So that's what I'm doing here. I'm saying that the velocity is equal to omega cross position. Okay, that's all I'm doing. All right, so this is your velocity equation, and again, it's planar motion, so you have 2 terms. You have your pure rotation, and you have your translation. Now we have to say, okay, well, how do I get my acceleration? Your acceleration equation would just be the derivative of velocity. So here you have, let me go back to black, the derivative of your inertial velocity of A is just going to be your inertial acceleration of A equals your inertial acceleration of B plus. Now I have to take the derivative of omega, which is in the k direction, cross RA with respect to B dt. If you are not up to par with your cross product operations, this might not make a lot of sense, but just know it's just an operation, okay? It kind of looks a lot like the dot product, but it's not. And I've actually heard some professors say, oh, we're just gonna do the dot product. Or I'm sorry, now I'm confusing. We're just gonna do the product rule. We can't do the product rule because this is a constant. And we just said that the RAB right here, we said that was a constant. And omega, in a rigid body, omega A has to equal omega B. By definition, in a rigid body, all the particles spin or rotate about a fixed axis at the same rate, okay? So they have to be equal to each other. So really here, we're not using a product rule. All we're doing is saying, what is the definition of taking a derivative of a cross product? And the operation states that you are going to take the derivative of the first cross your second plus the first term cross the derivative of the second term. Okay? It is not, well, I don't want to confuse you. We'll stop there. Okay, so what did we say VB was? We said that VB was equal to omega cross RA with respect to B. So we can kind of, let me put this down, give us some more room. We can say that the acceleration, as if I'm sitting on the inertial frame watching my airplane, the acceleration of some point on my airplane is equal to the acceleration of a different point on my airplane plus alpha cross RA with respect to B plus omega cross RA with respect to B. Okay. We derived, if we go up here, we derived this in 2 dimensions, and this was x and y with a unit vector I and a unit vector j. If you are in planar motion, that means that, and your planar motion is defined by x and y, that means your third axis has to be a z, and we give the unit vector for z, we give it k hat. So that means that this has to be in the k hat direction, and that means this one has to be in the k hat, and this one has to be in the k hat. And RAB, we defined up here as, where did we define RAB? Right here, some distance in the I and some distance in the j. So if I wrote this whole thing out, omega k cross omega k, it's a horrible k, omega k cross some distance in the I plus some distance in the j, and I worked that out, I would have omega k cross xi, so I would do omega x, k cross I is j, omega cross yj, that's going to be omega y, k cross j is negative I. Now I have to do that again, okay? And this is going to say omega times omega is omega squared, k cross, and then you have an x, and then k cross j is I, and then you have omega times omega, which is omega squared, times your y, don't forget that, k cross I is j, and that's positive, but you have a negative right here, and I forgot this, oh my goodness, k cross j is negative I, so you have a negative here. You can factor out the omega squared, so you have negative omega squared, and then you have xi plus yj, and we said that that was r with respect to b, so this is actually negative omega squared RA with respect to B, and that gives us our final acceleration equation. So we can say that the inertial acceleration of some point A is equal to the absolute acceleration of B plus alpha cross RA with respect to B minus omega squared RA with respect to B for planar motion. And it's not like planar when we say, oh, planar motion is translational and rotation. It's planar motion, meaning it's 2D. So you might want to say 2-dimensional motion. If it's 3, your body is able to rotate about more than one axis, which means up here, you see how I derived it where both, let me use a different color, where both omegas were, the body was rotating about k. Well, it doesn't have to be that in 3 dimensions. It could be omega k cross omega I cross xi plus yj plus zk. k. In that case, you have to leave it in this form, okay? You have to leave it in that form because you have to account for different frames. So this would be just alpha, omega, and omega, okay? That is how we get our relative equations when we're trying to describe a rigid body motion. What happens now when I say I want to describe the rigid body motion between two sliding contacts? Well, if you look up here, in the very beginning we said that RB was constant. It's not constant anymore, and that means everything below here is not applicable, okay? So now what we need to do is say, okay, well, let's rethink this. Now we have, let's build a mechanism that we can kind of build this off of, right? We have some external pin here that goes to an external pin here. We'll label that B. And then B is also on some rigid body that has like a slot in it. This looks ridiculous. Looks like a pickle. Okay, so this is all one rigid body, okay? And then you are going to have, say we have another ground over here, and then this guy is going to, it's not going to attach by like a normal joint. Like right here is an internal joint where B is connected to the screen body. Here, what it's going to have is like either some kind of raised like drum or a pin or something like that. And it's going to be like fixed inside of it, okay? Or it could be a collar like this, it doesn't matter. What matters is that the blue bar, its motion, and the green bar, its motion, is dictated by each other, okay, because of that slot. The motion is constrained, okay? So let's label some points here. This is going to be our point A, that's B. I'll label this C, D, and E. Okay, so my question for you, is A, B a rigid body? No, because A is not on the body. It's touching it, it's sliding. It's attached to body DE. So I could say that EAD is a rigid body undergoing planar motion. Actually, it's undergoing pure rotation. It's undergoing pure rotation. I can also say the same thing for body CB. It is also a rigid body undergoing pure rotation. But BA, this is two rigid bodies undergoing planar motion, undergoing planar motion, it should be like planar sliding contact motion. Let's say it that way. So it's going to say planar sliding contact motion, because now I can solve EAD and CD by using the equations that we developed up here. No problem at all, okay? Now if I want to describe the motion of A, I can no longer, because A is influenced by the rigid body B, I can't use that anymore. And that's because of this. So let's draw our vectors. If I wanted to describe, let's use a different color. Pink is not spooky. I'm going away from my theme, but that's okay. I'm going to place an inertial reference frame at C. We're going to call it O, because definition of pure rotation. This is in pure rotation. Any particles on the axes it doesn't rotate. Any particle off the axes is going to rotate about the axis at the same rate. So if I put it in the middle of that, I'm sitting on that axis, which means that that could be an inertial reference frame. Okay, let's locate point B, and that is its absolute position. Let's also locate the absolute position of A. That's a horrible position vector. And then I want to locate A with respect to B, because again, I still need to, if I'm observing it from point C or from my inertial reference frame, I still need 2 points to describe its rotation. So I pick my 2 points, and I'm going to do this. Okay, so there's one more thing that I need to add to this schematic in order to kind of make this work. I'm going to place a body fixed reference frame on here. And it doesn't matter, like if I put, so my inertial reference frame, which I have in pink, I can say that this is big I and big J. And then in this little moving frame, I'm going to just call it little j and little I. It doesn't matter, as long as you understand that they are variable, because this, as this body fixed, as A moves, the body fixed frame is also going to move. Okay, so it's going to go like this. You see the directions moving? The magnitude won't move, but the direction will move. So now when I write, when I say, okay, what's the absolute position of A? I can represent the absolute direction, absolute position of A by using my vector addition, which would be RB plus RA with respect to B. But this time, when I break down what RA with respect to B is, it's going to be some distance in the I plus some distance in the J. And this is little I and little j, because this is all, that whole term has nothing to do with my pink inertial frame. This is all relative. So that's saying the relative position between the two. And that means that both x and I, as well as j and y, are variables. So when I take my derivative, I get VA equals VB plus, I can represent that as VAB, like VA with respect to B, but this VAB is not the same as this VAB. This VAB was just omega cross R with respect to A. But now I have to, when I take this derivative, I actually have to use the product rule, because now my I is no longer a constant. So I have to do the derivative of the first times the second plus the first times the derivative of the second plus derivative of the first times the second plus the first times derivative of the second. Okay, so now VA equals VB. Let's look at some like terms here. We have an x dot and a y dot little j. If I say x dot I plus y dot little j, this is the velocity of the 2 points of interest, my A and B. That's the relative velocity between them. And we term that as V rel. Okay, so I can say plus V rel. Now I also have this guy and this guy. So let me pull them to the side. I have x di dt plus y dj dt. Okay. What is the derivative of unit vector I? Did we do that up here? No, we didn't. Nope, we didn't. Okay. So what is the derivative? Up here, we actually did do that. We said, what is the velocity? How can we represent that in pure rotation? And I said, well, it's just omega cross r. It's the same thing down here. If I have the derivative of a position vector is just, so say I have my position vector I, right? And it's in pure rotation, right? I'm going to say that I know my velocity vector is here, and that's perpendicular. This is velocity of I, which can also be written di dt. Then my third vector, because this is moving and it's going about the axes, is omega. I can say that the position vector I cross the omega vector gives me my velocity vector. So really, this would be x, the derivative of position vector I, which is basically velocity, is equivalent to omega cross position vector I, plus y omega cross j. Now, cross product rules state that you can distribute a scalar into any of the terms. It doesn't matter which term you choose. I am going to distribute it with the unit vector. So I am going to say that this is really omega cross xi plus omega cross j yj. Okay? And then I'm going to say, well, let me erase this. Well, whoop, whoop, whoop. All right, what am I going to say? I'm going to say that this is going to, if I work this out, I'm going to say this is in the k direction and this is in the k direction. What is omega k cross xi? Well, omega times x, and then I'm going to do k cross I is j. And then I'm going to do the same over here. Omega k cross yj is going to be omega yi in the negative. Well, this is the same as omega cross r a with respect to b. Don't believe me? You should. No, we can redo it. So let's do this. Let's say, well, let's work it out. We have omega k cross some distance in the I plus some distance in the j, because that's how we defined it up here, right? So if you work that out, you have omega k cross xi, which gives you omega xj. And then you have omega k cross yj, which gives you negative I. Guess what? It's the same thing. Told you so. So I can add omega cross ra with respect to b. And you can compare this, so this is our final equation. The only difference you have between the two velocities, one of a rigid body where you're comparing 2 points on the same body, and sliding contacts, is this vrel term. That's the only difference. You still have your pure rotation, your pure translation, but now you have an extra velocity due to the sliding, okay? So now we have one more job. We have to take the derivative of this. So let's write it down here so we can give ourselves some room. So we have to take the derivative of this guy to see how our acceleration is different when we compare 2 points on one rigid body versus 2 points on two rigid bodies in sliding contact. All right, so let's do it. First, before we start taking derivatives, we're going to want to expand terms. So we have VA equals VB plus VREL. We said VREL was x dot, this over here, if you can you see this? I don't know if you can actually see my mouse, but we have x dot I plus y dot j. So this is x dot I plus y dot j plus omega cross, and we stated that RA with respect to B was some distance in the I plus some distance in the j. Now I'm ready to take my derivative. So the derivative of absolute velocity is just absolute acceleration. And then we have, okay, let's get to our first term. We have two nasty terms that we need to take the derivatives of. Let's look at the first nasty term over here in the corner. We have x dot I plus y dot j. That was our vrel term. Our x dot and our I, our y dot and our j, they're both variables, which means we have to use the product rule. So we're going to do derivative of the first times the second plus the first times derivative of the second. And then we do the same for the second term, derivative of the first times the second plus the first times derivative of the second. Now look and see that we have some terms in common here. We have two double dot terms. Let's do the same thing we did for our relative velocities. If we take these out, we can say that this is the relative acceleration between the 2 points, right? Because x double dot and y double dot, that's just an acceleration, the double dots. So that's the first one that comes out, so I can put that down here. But we still have these terms here that we need to deal with, okay? So we have an x dot, and we have a derivative of a unit vector. Again, the derivative of a unit vector is going to be omega cross its position vector, plus, and then we have a y dot, and the derivative of a unit vector, which is going to be omega cross that unit vector's position vector. Okay, again, product rule states that I can distribute this outside scalar term to any inside term that I want, okay? So I'm going to go ahead and distribute that in. I'm going to say omega cross x dot I plus omega cross y dot j. This, if I, let's take a minute and actually do this. So I would have omega cross x dot, omega is in the k direction, so k cross I is j, and then over here I'm going to have omega cross y dot, that's omega y dot, k cross j is negative I. This is the same thing as if I said omega cross, what is x dot and y dot? Do you remember? It's v rel. Do you believe me? You're probably like, no, I don't. Okay, let's write it out. Omega k cross v rel is x dot I plus y dot j. Okay, so omega cross x dot I. You'll have omega x dot, k cross I is j. Then you have omega times y dot, k cross j is negative I. Look at that. Same thing. So that means that for my A, I can plug in the simple version, omega cross v rel. So these two terms, can you see what I'm doing? These two terms here come from the derivation of this v rel term. You get two terms because they're a variable, okay? So please don't leave it in this form here and take the derivative directly and say, oh, it's just a rel. If you did that, then you would miss this term. Okay, so don't, I know, we can't cheat, boo. Okay, so now let's take care of, we still have this nasty term here. So let's give us some room. This nasty term, oh my goodness, so this is gonna be plus something. So we have omega cross xi plus yj, and we need to take its derivative. Before taking its derivative, and trust me, I did this both ways. It is a lot easier if you do the cross product first and then take its derivative. Just take my word on it because I'm not going to show you both ways. So I'm going to say omega cross xi is omega xj. Omega cross y is omega yi in the negative. Now I am ready to take my derivative. Question, is omega a constant or a variable? It's a variable. At the distance between the two, in the x direction and the y direction, variable. And the unit vector direction between the 2 points, variable. That means I'm going to take the product rule 3 times. Well, 6 altogether. So I'm going to say the derivative of the first times the second and the third plus the first times the derivative of the second times the third plus the first and second times the derivative of the third. Next term it has a negative in front of it, so it's going to be the derivative of the first times the second and third minus the first times the derivative of the second times the third minus the first times the second times the derivative of the third. Now we are ready to find some like terms here. We have an alpha and we have another alpha. So let's take those out and see what that looks like. This is alpha xj minus alpha yi. This is equivalent to me saying alpha cross ra with respect to b. If you don't believe me, I can show you. So I can say alpha is in the k direction cross. We defined RAB in the beginning as some distance in the I plus some distance in the j. Alpha k cross xi is alpha xj. Alpha cross yj is alpha y negative I. This is the same thing as this. So in my equation, I can now add this term here. So I can say plus alpha cross RA with respect to B. I'm not done, because now I have to look at the other terms I have left. Let's find some more common terms. I have an x dot here, and I have a y dot here. So let's look at omega x dot j minus omega y dot I. This is the same thing as me saying, oh dear, as me saying omega cross x dot and y dot, we said was v rel, right? So we can say that this is going to be v rel. Don't believe me? I bet you believe me by now. But we can work it out. What's omega k cross v rel? We defined as x dot I plus x dot j. Okay, omega k cross x dot I is omega x dot j. Omega k cross x, this is the y dot, Dr. Rock, hello. You silly. I was bound to mess up sometime, right? plus y dot. Okay, now we're good. Omega k cross y dot j is going to give omega y dot negative I. Look at that. I'm never going to lie to you. So now I can add this term in. All right, let's add it in pink. So we have omega cross v rel. So this is going to be plus omega cross v rel. Later, I'll put these two together, but we're not done yet because we still have two terms left. We still have two terms left, and I'm actually going to do that in green because why not? Okay, so I have omega cross, the derivative of unit vector j is, I'm sure you know these now, like, yes, Dr. Walk, we've got this. Okay, so what is it? Did you say it? I hope you said it. Okay, it's going to be omega cross j minus omega y omega, yeah, I got that. Okay, omega cross I. Okay, so now I'm going to say, well, again, because cross product rules say that I can take a scalar and I can factor it into any term I want. I'm going to put those together. I'm going to say omega cross xj minus omega cross yi. And then, do I want to substitute them in? Sure, you can if you want, or you can leave them separate, it doesn't matter. But this is going to be equivalent to omega cross RA with respect to B. And the same thing like we did in planar before, if you are in two dimensions, you can say that this is omega squared RA with respect to B. This is our last term that we have to add to this ridiculous equation. This is going to be a negative. Minus omega squared RA with respect to B. I'm going to lasso this and see if I can bring it down. Okay, and then I want to bring that down here. And now what I want to do is clean it up. Let's clean it up. We have the absolute acceleration of point A equals AB plus A rel plus, I have this term and this term, that would be 2 omega cross v rel. Again, product rule, I can put that with anyone I want because it's a scalar. So I'm going to say 2 omega cross v rel plus alpha cross RA with respect to B minus omega squared RA with respect to B. Now, this equation, if you look, has the exact parameters that we got up here in a rigid body where the 2 points we were comparing were on the same body. We got the same terms. That's this term and this term. These terms, this is your acceleration in the tangential, which if you go back to your particle kinematics, acceleration in the tangential is defined by alpha r. It's just pure rotation. This one is your normal or your centripetal acceleration. And if you go back to your particles for normal and tangential acceleration, you will see that it is omega squared r. I know, funny how things work out. Pure rotation, baby. Okay, down here, guess what? Same thing. You will have your AT and you will have your AN or your Coriolis. But you have this extra terms. You have extra terms. This term, ooh, it causes a stink among people. Engineers, they say, oh, it's a correction factor. It's kind of like Coriolis acceleration. Go to someone in the weather, and if you tell them that that's a Coriolis acceleration, they will look at you like you have 3 heads. Please don't do that, okay? Read the room, know your audience. This is an acceleration due to sliding. So you should be asking yourself, okay, well, when does Coriolis acceleration come in? Well, that's our third topic. We can build another scenario. I can say that I have my inertial reference frame, and inside my inertial reference frame, I have a rigid body. And on my rigid body, I'm going to have a little spider. And my spider can move any way it wants, okay? It's not constrained to a motion. Up here, A is constrained to a motion. Down here, I will label my cute little spider A, and I will define a point on my rigid body B. And now I'm asking, my question for you is, what is the motion of A relative to someone standing away? They're the inertial reference frame. I'm just looking at this thing. Now I'm looking at, oh, what are those things called? A lazy Susan? Is it the thing like you spin and like the food comes around or whatever? Okay, whatever it is. We'll stick a turntable. We're gonna go with a turntable. Okay, you got a turntable and someone spinned it, right? And then all of a sudden an ant is on it and the ant is like moving around, right? You are looking at the ant. You can see that the ant is turning and walking. You can see this, right? The way you are going to describe its motion by locating its position, its absolute position, so this is RA, and you are going to have to locate some point on that turntable, so that's going to be RB. Then you have to say, well, how is my little spider moving relative to the turntable? So that's RA with respect to B. So now if we say, don't worry, I'm not going to go through a whole another derivation. Stick with me here. So if I say, well, I want to know the absolute position vector or position of my spider. Well, that is using vector addition is going to be RB plus RA with respect to B. This RA with respect to B is some distance in the I plus some distance in the J, and these are variables. So because of the way we defined R, the relative position, it's defined the same way as we did right, I don't know where we initially did it. I think it's right here. This right here, it is the same definition, which means everything from here out is the exact same. Here's the difference though. Look at your schematic. My spider can move any way it wants. The collar, it can't. It's constrained. It's constrained. You need to, and then, so what does this bring about it? Well, if it's not constrained, then you can say that this term is Coriolis. Because say if you get on a merry-go-round, like one like when you were a kid, did you ever get on the side of the merry-go-round and your poor little brother or your sister was sitting on it and you run really, really fast and you thought it was hysterical? Okay, think about you running really, 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 really fast and your poor sibling sitting on the merry-go-round. They are going to feel these sideways forces, right? That is the true Coriolis. Here's the difference, and I'm going to put the definitions up on the screen now. So first, if you are looking at planar motion, if you want to describe a rigid body's motion in an inertial reference frame, so I'm sitting and I'm fixed and I'm looking at my airplane, I can locate 2 points on that airplane and I can use relative acceleration and velocity to describe that entire body's motion. If I now have 2 objects, if I have a slider and I want to define the motion of this slider from my fixed position here, I'm just looking at it, I can use relative acceleration and relative velocity to do that, but now my R's are no longer fixed, they're variables, which are going to add 2 extra terms to my equations. Okay. And then your third option is you're going to have 2 bodies that are in motion with each other, but they can move free. They're not constrained. Their motions aren't constrained. So you are going to analyze the motion, the body's motion, by looking at a point on one body and a point on another body. And those points, again, are variable. The distance is variable between them, but they are free to do anything they want. They are no longer constrained. Okay, so that's the main difference. And in the free moving one, you have a true Coriolis acceleration. Okay, in your sliding contact, it's not really considered a true Coriolis. That was a lot. I hope that kind of makes sense and that you're like, I totally know the difference between them and it's good. The reason that I'm harping on this so much and that I think that it's super important is because when you set up your problems or you go out to industry, you're not going to be handed a problem saying this is sliding contact, go ahead and solve it. It's not like that. You're going to have to determine, you know, are their lengths changing? Is this an inertial reference frame? Is it a moving reference frame? What do all these accelerations mean to me? If you know the fundamentals and you know where we get the equations, you'll know how to start and you know how to develop it. I thought it was so important that I made my class demonstrate these. So I made them do a ghostly gyroscope where they held on to a rigid bar and they had to maneuver around this maze, okay? And they could only use planar motion. I also made them do a slippery slopes of horror. That's where I was demonstrating what slide and contact looked like, and I had someone sit in a chair, and then I had like a movable lane, and I had an external force. Another student pushed the person in the chair, and it had to basically follow the lane. And then the last demonstration that I made my students do was the witch's coven. So a bunch of students would get together, and then they would start spinning, and this like turning motion was representing a turntable. And then I had this little lonely ghost. It was like I think I called it a spirit, a wandering spirit, went into the circle, and it walked anywhere it wanted. That was demonstrating the turntable with my spider on top of it. I hope this either made you laugh or it made you learn. Either way, thanks for sticking with me to the end of this video, and I will see you in my next.